trip to the Stanford accelerator that was when I was going to schedule the midterm, and the fact that some people are going to that, I decided to move the midterm up to 2 weeks from today rather than 2 weeks from Tuesday. And so because of that, and because of our long weekend, we won't really have time to squeeze in another quiz. So we're going to cancel the quiz that we're going to have on electrostatics. And so some of you may be thinking, well, that's great, but the reason why I do these quizzes is to help get you ready for the midterm. And so I am concerned because this is more difficult subject matter that we're about to tackle. And so you want to make sure that you get plenty of practice with this. In order to assist with that, next week after we get back from our long weekend, during lab next week, we're going to have a pretty extensive problem-solving session that works, for the most part, with calculation of electric fields using calculus techniques. And so those are the things that I found in the past have given students the most trouble. And so we'll have some interactive stuff, and hopefully we can get a couple of the embedded tutors to help us during lab as well.
Could we get a copy of what we're doing our quiz to practice on instead of actually having a quiz in class?
The kinds of questions that I'm going to be throwing out next week during the lab prep are going to be very similar. So you're going to get a good exposure to the kinds of questions. But you know, I found that it's not so much the wide variety of problems that throws people off, but the basic operations. I, a lot of times, haven't deviated very much from my lecture examples and from the problems you see in the book. But a lot of times, that's still not enough. A lot of people just don't have a clue as to how to even start these problems. And so I'm going to spend some time on that today. This is kind of our introduction into electric fields for continuous charge distributions. But there's a little bit that I still want to look at in terms of the construction of electric fields. Because if we don't really understand what an electric field is, then doing these calculated computations to figure out what the electric field is aren't really going to mean anything. So we don't even know what it is that we're calculating. Okay? And so let's just review a little bit how we calculate an electric field. It has a magnitude at a point in space, points away from positive. The magnitude of E is kq over r squared, where this is our charge q. So that would be the same at any distance r away, where r is that same value. It's going to have that same magnitude, and then the direction will be times some unit vector that points straight away in the r hat direction. Points away from positive and toward negative. This distance again is r, and this is kq over r squared, but pointed toward negative and away from positive. And then these electric fields add like vectors. And so one thing that we can say is so far we've been looking at electric field lines that are straight. But what happens if we start adding electric field vectors together from two different charges? So that would be the case, say, with a dipole. Okay, let's take a look at a dipole for a second. The electric fields point straight away from positive and straight toward negative. But in some in-between position like this, the electric field that points away from charge 1 and the electric field that points toward charge number 2 are going to add up in such a way as to cancel out the vertical components if we're at the midpoint between them. So this distance, say, is L to the midpoint, and this distance is L then the lengths of these vectors will be kq over L squared, but they won't be pointed in the same direction. One will be pointed away from positive, the other will be pointed toward negative. So we can decompose that into x components that add and y components that cancel. So what we notice then is that the tangent to these electric field lines along this line of symmetry only has a horizontal component, but it's going to decrease in size as we get farther and farther away from the center. And that electric field will be a maximum value at the midpoint. And then we'll drop back off again, but it will be horizontal, essentially a tangent to the electric field line. And so this is an example then of a curved electric field. And so, well, what if we went to here? Well, here we have an electric field at a point, be pretty big because it's close to charge 1, and we have another electric field that would be shorter that would point toward charge 2. And so this would be the resultant vector then, E. What we would notice here is that it's still tangent to the electric field lines. Okay, so if we add this vector E1 and this vector E2 together, the head-to-tail addition vector sum will be a tangent to the field at that line. And similarly here, if we take an electric field vector that points away from charge 1 and points toward charge 2, because it's closer to charge 2, then the resultant electric field will again be a tangent to this electric field line. And so one thing that we can notice then about electric fields in general is that the direction of the resultant electric field is a tangent to the electric field line. And another thing that we can say is that the density of the lines is proportional to the strength of the electric field. So in other words, the electric field is stronger in here, which we can see just from drawing the vectors. See here that no components of the electric field are canceling. So you've got the E1 that's pointed away from charge 1 and the E2 that's pointed toward charge 2. I've already done that numerically as an example. But we see that as we start moving farther and farther away, the electric field is getting smaller because we're farther away from each charge. And associated with that, we see the spacing of the relative electric field lines is getting farther apart. So we have more density of the field lines in here, but this goes like 1 over r squared. So we expect more density closer to the charge. And if you could take the density of all these lines that intersect here, you'd have a density of infinity, which isn't going to really happen in a true sense if we think of these things as having a finite size. But nevertheless, mathematically, if we take the limit of 1 over r squared as r goes to 0, we're going to get infinity. And so the density becomes infinity where all the lines converge. And so the lines are getting more tightly packed in here and would approach infinity as we get really super close to either one of these charges. And then would spread out farther away. If we have a uniform electric field, then the spacing of the lines is going to be constant. And so this is an easy one. This would be the positive side. This would be the negative side. If the electric field is constant, then we have no difference in the change in the direction or the spacing of the lines. And a tangent to a straight line is still just a straight line. So we know what the direction of the electric field is in this simpler case as well. So electric field lines then are a tool that helps us to understand what is actually a more mathematical process, but we can get a feeling conceptually for what's going on from the density of the lines and from constructing tangents to the electric field lines. Now remember that this could be any two charges. One could be a Van de Graaff that we had in class last time, and then if we hook that up so that the ground wire went to another Van de Graaff, and then we just shut this Van de Graaff off, then you could have equal but opposite charges on both of those, and then you would get a dipole field. A dipole field, as we've seen before, with any kind of a charge separation. Like with the water molecule that we looked at before. Now if you have an asymmetry in the amount of charge, that means that some of the field lines are going to start on positive, but if there's twice as much charge, now, in a continuous case, we've got an infinite number of field lines. So we're just drawing a few representative ones. That's an important point to bring out here, is that we're trying to get the sense or the flow of the electric field from these lines. But we're just drawing a few of them, and so we're talking about relative spacing here. But we notice that some of these field lines end on negative, but depending on how many of these you've drawn, you're going to have an equal number of field lines that have got to find some other negative charge somewhere in the universe to terminate on. Because every positive charge will have a field line that terminates on a negative charge somewhere else in the universe. Okay, but you can still justify the strengths and the shapes of these electric field lines just by taking a tangent at one point here, say at this point. That's the tangent. That's going to be the sum of E1, which is going to be bigger. That points straight away from positive like this. And E2, which is going to be smaller. Because it's farther away from charge number 2. But they'll add together to give you a tangent to the field line that is the same as the slope of the field line at that particular point. So are there any questions about how electric field lines are being used to help describe the electric field? Okay, remember, this is a whole chapter now on electric field, so we don't want to be mixing this up with electric force, or everything that we do will be completely built on sand that will get washed away. Next thing I want to look at is, well, we've just been doing this so far for point charges. But what about for here's another, that's a good, just kind of general idea. What you do with electric field lines, you draw them tangent to the electric field at a particular point, it's just a tangent. That gives you the direction. And then here, we can see that the force, the electric field lines is this way. The force on a positive charge will be to the right. Force on a negative charge will be to the left. And so we know that F is QE. That's a very basic, important relationship. So a positive charge means that F and E are in the same direction. A negative charge means that F and E are anti-parallel. But another way to look at this is to say, okay, well, I know what's causing this. It's an infinite plane of charge over here that's positive on this side, that's negative on that side. So I know that positive is going to attract negative and positive is going to repel positive. So that gives me the direction of the force right there. I don't need the mathematical description. That will help me verify it, that what my intuition is telling me is true. But I don't need that to get the right direction for the force. I know here that negative will attract positive and negative will repel negative. And so that will drive the negative charge to the left or in the opposite direction from the electric field. So this is the utility then of the electric field, is it connects us to the force. The force is a measurable quantity. And there are other important uses for the electric field too. It turns out that the electric field, when it changes, it can produce a magnetic field. So there are very basic relationships between electricity and magnetism that deal with the electric field. We also saw last time in lab that you can get the voltage from the electric field over a distance. And so that's another application that we'll be looking at later. But electric fields are very critically important, but not the same thing as forces. So next, what I want to do is look at E-field calculations for continuous distributions of charge. Okay, and the simplest problem I know how to do is a ring, a charged ring. Okay, so we would say this is a continuous distribution of charge because the charge is no longer at a point, but it's distributed around a thin ring. And so let's say that my goal here is to find the force, or I'm sorry, the electric field along the axis of this ring. Let's say that there's a total charge Q distributed on this ring. So my goal then is to find the electric field as a function of x along the axis of that ring. Okay, where x is the axis, intersects the plane of the ring at a 90-degree angle. So it goes right through the center. So we're interested then in the electric field here at this point x. We want to know what it is. But we have to extend our ideas on point charges because we saw before, and this is something again that I'm going to show is true in chapter 23. But for the moment we're just taking this as being fact, that for a point charge, E is equal to K Q over R squared. Times some unit vector that points straight away from that charge Q. Okay, so that's good for a point charge. But what about for a continuous distribution of charge? Well, then what we're going to need to do is find dE for a small amount of charge dQ. And so here, I'm going to just pick randomly on this charged ring an element of charge. I'm going to say, okay, I want to know what the little bit of electric field is due to that little bit of charge at my point P. Why? Because then I can integrate this. To get the total electric field by adding up the effects of all of the little dQ charge elements. Okay, and so if I do that here, then I have to take the differential of both sides of this equation, giving me dE is equal to K dQ over R squared. Where this is my dQ, this is my R, and so here then I'm going to have that point straight away from, and let's say it's a positive charge there, so this is my dE. Now it may sound funny to draw a finite length for an infinitesimal quantity. But it works okay. These are, we could imagine and we're taking the limit as dq approaches 0, so that this is actually a finite amount of charge, and that this is a delta E, which is a finite number. And then we eventually then just take the limit as delta E goes to 0 to get dE. Okay, but this is where the calculus comes in, is that we have to add these up. By adding them up, I mean integrate. I have to integrate all of the effects of the little charge elements to get the total. So dE here is going to be k dq over r squared. Now let's write r in terms of given quantities. That's going to be the square root of x squared plus a squared squared. Or dE in this case, k dq divided by x squared plus a squared. And so all you have to do is add all of these up. But we've got a problem here, and potentially we have two problems. We can't just add these things up without taking these two possible difficulties into consideration. One possibility is that could mess this up, is that not all the r values are the same. Is that the case here in this problem? Do we have different r values? If we start looking at all the little dq's, I'll take one maybe over on this side. Has that got a different r value than that one does up there?
No.
No, it doesn't. All of these points on the thin ring have a distance that's the same. So this is the square root of x squared plus a squared, and this is also square root x squared plus a squared, where x is some distance along the axis. So that's not a problem here, and that's the reason why I chose this example first, is that this simplifies the math considerably if all of the distances are the same. And so that's not true in the ring example. But it is true in most other examples. The second difficulty, and this one we will have to deal with, is that some of the components of the d's are going to add and some will cancel. And to see which ones add and cancel, we need to look for symmetries. Now this is going to take on a lot of different forms. The kind of symmetries are going to differ from problem to problem. But in this problem, the symmetry that I want to examine is that if I choose oppositely opposed dq's, their vertical components will cancel, and the horizontal components will add. How do I know that? Well, because I can choose any pair of points, and I'm going to get the same geometry as I'm getting here for these two. And so here, if this is dE and that's dE, then this is going to be dE cosine theta. That's theta, and that's theta, and that's theta. And this component is going to be dE sine theta. this is just our normal vector decomposition. Same deal down here. dE sine theta and dE cosine theta. So we see that the dE sine theta components cancel and the dE cosine theta components survive. Okay, so that's what we're interested in here then. For the integral of dE, it's going to be the integral of dE times the cosine of theta, not just dE, because I'm losing some of my components of dE. And so what would it be at the center? 0. Good. Because at the center, the electric field will point straight away from this one and straight away from this one. So the whole thing is just the vertical component. So it completely cancels if you're at the midpoint. But as you get farther and farther out, you get more of a surviving dE cosine theta component. And then I can do that for this charge and that charge too. On this side and that side, that's going to send off E field vectors that look like this, but then the sideways or vertical components will cancel, and it'll only be the horizontal components that'll survive. So I can do that for an infinite number of different pairs, all the way around, and this component is always going to cancel, and this component is always going to add. Can everybody see that geometry? That's critical that you see that geometry, because if you don't, this is one of the easiest problems I know how to solve using calculus. And so that means that the other ones will be not real solid if you don't have this picture in your head as to how this is working. And don't just try to force the math without a good picture. It's totally contingent on having a good picture. So let's go ahead then and see what we can do with this. E then will be the integral of dE cosine theta. Okay, and so that'll be k dq divided by x squared plus a squared. That was my dE. I got over there times the cosine of theta. That's x over square root of x squared plus a squared. And so again, we've done this before, but we did it before for point charges. Remember when we did this for point charges? Then we got a dE, or a dF, if we were to have a charge there. It's either dE or dF cosine theta, dF sine theta, and these angles we can get from the geometry of the triangle that has the physical links contained within it, because vertical angles are equal. Even though we're looking for these angles are the same as these angles, and because all the angles are the same, this triangle is similar to that one, and so therefore has the same ratio of its sides. Okay, so this is our cosine theta, and then we're going to integrate. Okay, now, difficulty 1 comes into play in most problems here, because q is going to be a function of distance. So that means that we'll in future problems, nearly always have to write our dq as a function of x. But we don't have to do that here because it's constant. So what we can do is just pull out the kx divided by x squared plus a squared to the 3/2 power, and just integrate out all the little dq's from 0 to big Q. Okay, so when we integrate the dq's, we just get the total charge. Here, this is going to be one little dq. Here's another one, here's another one, here's another one. And it doesn't matter how finely we divide them. We can sum them up if they are a finite number. But if it's an infinitesimal quantity, we can just integrate. And that just gives us the total charge Q. So the electric field E then is equal to K Q X divided by x squared plus a squared to the 3/2 power times some unit vector that points in what direction? Good. So that would be our I hat direction. We can set up an I hat, J hat coordinate system like that. And then we would write this as some I hat vector like that. And that would be our answer. And so we did it. We found the total electric field. It points in the x-axis to the right and is equal to kqx divided by whatever x is squared plus a squared raised to the radius of the ring to the 3/2 power. Any questions about that?
So if you wanted to find like the magnitude of E there, you would just do it for the sine component and then take the square root, like put it into the vector form and take the square root of the magnitude.
Well, the magnitude of E is just this. So that's not changing. The magnitude of E is going to point in this direction because when we've added up all the little dq charge elements, we've canceled out the vertical components. So this is the magnitude already times the direction. Any other questions? Yeah.
Could you substitute out dq for something in terms of circumference? If
You could. You could write dq as charge per unit length times some little bit of length, which would be 2 pi a. Let me see. What that would be? So that would be q times the integral of r d theta from 0 to 2 pi. This would be a charge per unit length around this thing times the little bit of arc length distance. And so that would give you lambda times 2 pi r, but lambda is equal to q over the length 2 pi r. So you could do that. I'm not doing that here because it's not necessary. And it just creates confusion at a point when I don't want to do that. But we will need to do this soon, very soon. And for almost every other problem, we'll need to do that. Okay, where this would be our linear charge density. And that being units of coulombs per meter. So that'd be charge per unit length. So we can define lambda as charge per unit length. So if we know the total charge, and we know the total length, then we can get lambda. Lambda is just total charge q divided by total length, which is 2 pi. In this case, r is a. So I put in an a there. Any other questions? Yeah.
Would you mind explaining again? You said for dq, for this example, we could keep it constant, but for other examples,
What constant? I didn't say I could keep it constant.
The dq?
I didn't say dq is constant.
What would you do for it in other equations?
I have to do with what?
The dq.
dq would have to be written as a function of r.
Oh, okay.
If situation 1 is pertinent, which it will be usually.
Gotcha.
I need to write it as a function of r. But I don't have to here. So let's just see if we can understand this first without getting it all garbled up in a bunch of other stuff. Is everybody okay with this so far? Okay. Next, what I want to do is just take this result and ask a quick question, just to see if this is something that's interesting to us. What is the force now on a charge little q placed so now I'm going to take all of this away. So we already have the electric field. The electric field is equal to K big Q over x squared plus a squared to the 3 halves power. But we know that, and so that's E here. But if I put a charge there now, that's when we get a force. Only when I put a charge now at that location do I get a force. Only an electric field up to this point. It's like a potential for force, but it's not the same thing as electric potential, but it's like a potential to produce a force on something. It's like imagine a stream flowing along. But there's nothing floating in the stream. And then imagine take a ping pong ball and throw it in the stream. The ping pong ball is going to get swept along with the river. Okay? That if you just dropped the ping pong ball down and there was no river, the river would dry, the ping pong ball wouldn't feel a thing. It's when you throw the ping pong ball into the stream that the stream carries it along. So imagine the electric field to be like a stream that's coming away from these charged particles. And then you drop this ping pong ball, and that's a charge that then feels that force. And that force, F, is equal to QE. So that's going to be K little q big Q times x divided by x squared plus a squared to the 3 halves power. Okay, so let's evaluate this now at x equals 1 and a equals 1 meaning. Just so the numbers come out easy. And let's say that little q is 0.5 times 10 to the minus 5 coulombs, and big Q is equal to 2 times 10 to the minus 5 coulombs. Just so the numbers come out kind of easy. Then I can figure out the magnitude of the force as 9 times 10 to the 9 Newton meters squared per coulomb squared times the product of the charges. That's going to be 0.5 times 10 to the minus 5 coulombs times 2 times 10 to the minus 5 coulombs times x, 1 meter, just making the numbers easy here when I plug it in, divided by this distance squared. So that's going to be 1 squared plus 1 squared to the 3 halves power. Or that's 2 to the 3 halves power, which I believe from last time was 2.83. So then this is going to be 9 times 10 to the minus 1 divided by 2.83. That's okay. So that gives me 3.18 times 10 to the minus 1, or 0.318 newtons. So that's my force then on a charge that was placed at this location. So that's a physical value for a force. Then if I wanted the acceleration, I could say F equals ma, and then I get the acceleration as this force divided by the mass. But here I started with the electric field. I figured out what's the disturbance in the space before I put the charge there, like the stream that's flowing along. You know, if it's a big stream, then it's like a big electric field. I throw in a slow stream, if I throw a ping pong ball in it, it's going to move slowly. If it's a fast stream and I throw a ping pong ball in it, it's going to move faster. So the electric field then is controlling the flow of these electric field lines, which then take that charge and produce this force on it. So it's not exactly what's happening, but it's close enough to give you a picture for it, I hope. Are there any questions? Okay, next, let's find a charge Q that I can put at the center so that the electric field is 0. And let's just find this as a function of x, so we don't have to punch out numbers. So here's my E of x at some distance x away. No charge there. But now what I'm asking is, if I put some other charge, little q, at the center, what is the value of that charge, little q, so that the electric field at this point is 0? So in other words, this is going to be, due to this charge, I'll call it charge 2, it's going to be E2. And due to this ring, I'll call this E1. So now E1 is the electric field due to the ring. E2 is the electric field due to the charge that's at the center. And so what I'm interested in then is getting a contribution due to E2 that's going to cancel out E1. Anybody have a suggestion on how I could solve that problem?
Set the two e's equal to each other.
Good. Set the two e's equal to each other, and then solve for the charge. Very good. That's exactly what we want to do. So we want E due to charge 1, the magnitude of it, to equal E due to the ring. E ring. And then this is E2, that's the point charge. So can I do that for the ring? Well, yeah, I already did that. So I just put that in on the left. It's going to be K big Q x over x squared plus a squared to the 3/2 power. And I'll set that equal to, over here, at this distance, that's x away. So that's going to be K little q divided by x squared. Everybody see where that came from? This is just a point charge at the center. But what does the sign on that charge have to be? Opposite or what? If this is positive charge up here, let's assume, then what kind of charge is this going to have to be? Negative. Okay, so this is going to have to be a negative charge. So if I'm doing this using the absolute value, then I'm not putting that negative in, and I'll have to get that out later. And I saw that some of you, when we did this problem, and you figured out the point here, you had one of these forces with a negative sign equal to the other one with a positive sign, and then somehow magically came up with the right answer. But you get an imaginary number for x when you do that. And so you're killing the minus signs when you set these equal, and you've got to put them back in at the end. So that's critical. And some of you made that mistake on that last group quiz. So you don't want to be making those kind of mistakes now, because we've got the calculus to worry about too. We need to keep up with all that stuff. Okay, so now the k's will cancel. And so I can solve for little q in terms of big Q. That's just going to be equal to big Q times x squared divided by x squared plus a squared to the 3/2 power. Huh? Oh, x cubed. That x is still, so it's x cubed. There's still an x there, x squared, bring that up. That becomes x cubed. Okay, so that's the charge at the center, but it's got to be negative. So whatever big Q is, it's got to be the opposite sign from big Q. And that would be the charge at the center, which would make the electric field 0 at this point. Then if I put some other charge at that point, what's the net force on that other charge? 0. So any other charge now, I can bring in any charge I want. I can put it at this location. I won't feel any force because the forces are balanced between the two. Any questions about that? So far, math isn't too bad. The visualization of what's going on can sometimes be challenging. All right, what next? Well, for the next problem, what I'd like to do is take a look at a line of charge. Now, for a line of charge, first of all, we have to look at how we're going to calculate the electric field with respect to that line. So let's do it along the axis of the line. Okay. So let's say there's this length L for this line of charge, total charge big Q. Distributed uniformly along the length. Now, if it's not uniform, then you've got another level of abstraction to deal with because it's a variable charge density. I'm going to start with just constant charge densities. We may look a little bit at variable ones, but not that much. Now, let's ask, what is the electric field at a point D away from the right-hand side? So what's our procedure for doing this? Well, first of all, we would need to keep in mind our two possible difficulties. One is that the different dq elements may be different distances away. Is that the case here?
Yeah.
Yes. Every dq is a different distance away from this point. So that's a problem. Do I have problems with the components adding and canceling? No. No problem with that. All the DEs point in the same direction. So I don't have to worry about the components in this problem. In the last problem, I didn't have to worry about the R values changing, but I did have to worry about the components. So in a more general problem, you have to worry about both. But this is my second easiest example that I can think of, is one that only involves the complication of the fact that the different x values, or r values you could call them, from dq to the point that we're calculating are going to be different from each other. Okay, so how do we start with this? Well, with all of these problems, draw a random dq somewhere on the object. And then label how that relates to DE and to your distance. Now, since all of these distances are in the x direction, I'm going to call Rx for this problem. But I don't have to. I could call this R if I wanted to, but R is in the x direction. If I had it oriented like this, I might call R Y rather than x. But it's in whatever, that would just be the same problem turned sideways. But for this problem, I'm just going to call my R value x. because it's pointed in the x direction. And now I can do my little dE. That's going to be k dq over x squared. But I can't just integrate the dq's the way I did in the last problem. Remember in the last problem, I just summed up all the dq's and I got q total. I can't do that here because each dq is a different distance away. So that means that dq, and this is so important. This is what I try to drive home, but this point somehow escapes comprehension. And I'm just trying to think of a better way of explaining it if I can. The dq's must be written as a function of x so that we have a function of a single variable. Because we can't integrate this thing unless we try to do a double integral or something. That's not going to work very well here anyway. So we want this as a single integral, so dq must be written as a function of x. And then we can integrate. Only then. We could get away with not doing that in the last problem because dq wasn't a function of the distance, but now it is. So now we've got to do this. So what's the best technique? Well, the best one that is also outlined for you in the book is we want to introduce what we call the linear charge density. And then we can say that our little bit of charge, dq, divided by a little bit of distance, dl, is equal to total charge over total length. So that's my lambda. I can write it either way. I can write it as dq dx, or I can write it as total charge over total length. Why? Because charge per length, if I cut the charge in half, and I want to know what the charge per length is, I've got half the charge, but half the length. If I cut it in half again, I've got a quarter of the charge, but a quarter of the length. If I cut it in half again, I've got an eighth of the charge, but an eighth of the length. So I can keep subdividing it like that, cutting it in half, until finally I'm all the way down to the limit as delta x goes to 0. That's essentially what I'm doing here. I'm saying delta q over delta x in the limit x goes to 0 is just dq dx, but it's a constant. The slope of charge versus x is a constant, and that's your lambda. So this is my constraining function. So important to understand this. What does that mean? It just means here I've got a function of two variables, but I use my constraining function to write one in terms of the other, so that I can write it as a function of one variable that I can integrate. So I can say then that dq is equal to lambda dx. And this is what goes in here. Once I've done that, then the integral is somewhat trivial. But understanding that that's what is being done seems to be a huge stumbling block for a lot of students that I've tried to teach this to in the past. So this is the really critical step. And so you don't want to just gloss over this or, yeah, I'll write it down, I'll think about it later. You need to understand it now. This is, we're building off of this, and everything else is going to require that you understand what we just did here. So instead of writing this as dq now, I'm going to write this as lambda dx. And now I can add up all the little lambda dx's all the way out. Are there any questions about that so far? Everybody good with that? Really? Okay. So let's do that. dE then is equal to k lambda dx over x squared. Now our limits of integration are not going to be 0 to x, because that would mean that the edge of the rod is right here at the point where we're calculating the electric field. So what are my limits of integration?
0 to L.
D to what?
0 to L.
No. 0 to L would put the electric field here. Then you would be starting, the charge would be starting right on it at a distance of 0 away, and I would get infinity.
The limits of integration for the left integral? Or for the right?
Well, we're adding up all the dE's, and so this is the critical one here. We know that the integral of dE is just E. So this is the one. That's the only one that we're interested in. That's the integral. That's the one and only integral. That is symbolically equal to this. But this is the only thing that's significant. So what are my limits?
0 to D.
0. I put that in here. I'm dividing by infinity.
Right.
It diverges. It's not an infinite electric field.
D to L plus D.
We start where?
D.
D. Good. We start at D. That's where the charge starts. And where do we finish?
L plus D.
Good. L plus D. Those are my limits of integration. You're not adding up charges in here because there aren't any charges in there. You start here. That's when x equals D in this equation. And then you keep going until you get to this distance away from this point, which is D plus L. And that's when you stop adding. Okay, so that's super critical to understand that those are the limits of integration. In a lot of problems, you go, oh yeah, let's just plus a constant, da da da. No, this is the problem here. If you don't get this right, it's completely wrong. So let's go ahead and solve that. For this problem, say that total charge is 10 to the minus 5 coulombs, and the total length is 1 meter. So if that's the case, then I can say that my lambda is just, even though it's dq dx, I can also write it as total charge over total length. And so that gives me an expression for lambda. So that's going to be 10 to the minus 5 coulombs per meter. That's my lambda. And so when I want a value for lambda, later on, I'm going to put that value in here. I'm going to leave it as lambda for the moment, though. I'm going to pull the constants outside of the integral. And I'm just going to solve for what dx is over x squared. So this is just like the simplest math problem that you would ever get. You go, there's got to be something more than this to it, right? If this were in a calculus class. But because it's in a physics class, we've got to understand what it is that we're doing. And so that's the level of abstraction that makes it more challenging. Question? Keep going. K lambda, dx over x squared, what's the integral of that? That's equal to x to the minus 2 plus 1 divided by minus 2 plus 1, or minus 1 over x. Does that look right? Are you okay with that? Okay, so this is going to be k lambda times minus 1 over x, evaluated from d to d plus l. So what I've done then is I've basically taken all these little charges and I've added them up. And so let's do that. Here, we can write this then as k lambda times, and then here I'm going to reverse the order of evaluation. So this is going to be 1 over d minus 1 over d plus L. So I did two steps at once then. I had a minus sign out in front. Probably should do it. Minus k lambda times 1 over d plus L minus 1 over d. And then I just multiply that through by minus 1. And that gives me a positive quantity because this is a bigger number and I'm subtracting that away from a smaller number. So that means I'm going to get a positive value. And that makes sense because all the little d's point in the positive direction, positive x direction. So that's looking pretty good. And so now I'm done, but I'm going to tidy this up a little bit. No, let's see. I could find a lowest common denominator. That's not really necessary. I'm just going to plug in. Okay, so let's say that L is 1 meter and D is 1 meter. Just so that the numbers are super easy to evaluate. And this is going to give me 9 times 10 to the 9 Newton meters squared per Coulomb squared times lambda. That's total charge over total length. 10 to the minus 5 coulombs per meter. Should write in the units. Times 1 over 1 minus 1 over 2. Okay? Because D is 1, B plus L is 2. So that's just 1/2. So that gives me 9/2 or 4.5 times 10 to the 4 Newton per Coulomb for my electric field. So that's the magnitude of the sum of all the little dE's here. Due to all these little charges, gives me E is equal to 4.5 times 10 to the 4 Newton per Coulomb. Now if I want to put a charge there, I can say, well, Q times E is going to be the force on that charge. But this is just an electric field so far. Any questions? Okay, so what made this one the second easiest problem that I can do is that it didn't have any components that were canceling. They were all adding up. But I did have to write my constraining function. So instead of having just a dq in there, I replaced dq by lambda dx. Lambda's a constant. So now I've got dq written in terms of my integration variable. And then I can proceed to do relatively simple integral to get the final result. Any questions? Okay, now there are different variations on this, of course, but what I'd like to focus on today are a couple of them. And so these, I don't have formally written out, but I'm going to put them up on the board, and I'd like these to be due as for extra credit along with your lab assignment this week. This will be for a possibility of 10 points extra credit on the lab. And there'll be some more extra credit problems that we'll do during lab next week too. But we can just think of this as being kind of a warm-up for that. And what I want to do is try this problem. for this problem, let's say that instead of having a full-on circle or ring of charge, let's say we have a semicircle of charge. Radius A and total charge big Q. Let's find the electric field at the center. So what do we do? Well, for this problem, again, in all of these problems, we want to look for symmetries. So in this problem, let's take a look at a little dq charge element. It's going to be a certain angle theta away from the horizontal. And the reason why I'm choosing this horizontal axis is that this is an axis of symmetry between the top quarter circle and the bottom quarter circle. Okay, so associated with this charge, and let's assume that these are positive unless otherwise indicated, I'm going to have a little dq that's going to point down, that'll produce a little dE that's pointed down. That's my dE due to that one. Now the reason for choosing this axis of symmetry is so that I can go an equal angle theta below. And then I can pick off these dq's in complementary pairs. And so what I'm seeing here then is that this dq, this kind of symmetry may look a little bit familiar from what we did before. But that was along the axis of a complete ring. Here we're just looking at the center. Now, if I wanted to go farther out, the break in the symmetry of not having the full ring is going to make it a lot tougher problem. If I try to find the electric field somewhere out here on the axis, a distance x away. But it's tough enough just to find it at the center of the semicircle. And so we know that if this were a full circle, the electric field would be what at the center? Zero. Right? We had before, E was equal to K Q x over x squared plus a squared to the 3/2 power. So if x is 0, E is 0. Right? Doesn't matter what the denominator is. X is 0, E is 0. But you can see that too, just because there would be some point on the other side that would cancel out the electric field due to this one. But by slashing off half of that semicircle, we still have symmetry, but we don't have as much symmetry as we had with a complete ring. And so we're not going to get an electric field that's 0 at this middle point, but it's going to have a cosine theta component that's going to add, it's going to have a sine theta component, it's going to cancel. So what we need to do then, and you're going to finish this problem up, and I'm going to give you a couple others that are variations on it in a little while. But I'm going to set this one up for you. And so here, first we need to know what dE is for each one of these little dq's. That's going to be k dq over a squared. So this distance a is not going to change. But in this problem, what is changing is that the q's are different angles away. And that controls how the components cancel. So we still do need to write a lambda in this case. So what we want to do in this case is say that lambda, our our charge density is going to be total charge divided by total length. What's the total length?
IR.
Good. Pi a for this problem. So that's going to be my lambda. And then I can also say that that's equal to dq d arc length, where s is arc length. So we know that s is equal to r theta. So ds is r, in this case a, times d theta. Why am I doing that? Well, because the way that the electric fields cancel is a function of theta. Here, when theta is 0, they don't cancel at all. These two pairs, which are infinitesimally close to each other, completely add up. But when we're up here at theta equals 90, they cancel out completely. So that means that we need to write q as a function of theta in this case. Okay. And so, but what are we going to be integrating with respect to? Well, for each dq, we've got this, but dE total is going to be k dq over a squared times the cosine of theta. Okay, because the sine theta components cancel. Okay, so now I'm starting to see why I want my lambda as a function of theta. But what's ds? It's a d theta. So therefore, dq then, instead of being lambda dx, it's lambda d arc length, which is lambda a d theta. So now I've written my dq as a function of theta, and that means that I can now integrate cosine theta d theta. So that's my strategy then, seen here, that as I change my angle, I'm changing the components that are adding and canceling. So that means it has to be an integral over theta, but with a constant value for r. So this is another variation on this. And, you know, there aren't that many variations. We've seen 3 so far. And then we'll be looking at combinations of all of these. But this is basically it in terms of the basic ideas. But then we have to apply them in problems that get a little more complicated as we go. Okay, so d total then looks like this. And so therefore, E is going to be the integral of k a d theta cosine theta over a squared times lambda. Does everybody see where that came from? We have lambda a d theta as my dq. Here's my lambda a d theta. Here's my k. Here's my cosine theta. The r isn't changing, so we can keep that constant. And so what I want you to do from here is evaluate, choose your limits of integration and evaluate. Get a final number. Let's say A here is 1 meter. Q is 10 to the minus 5 coulombs. And I think that's all we need. We just need the charge and the A. And so choose your limits and get a number. So we'll call this one number 1. For number 2, what I'd like you to do is basically the same idea, but for a quarter circle. Find E here for a